Good afternoon, everyone. Thank you for being here today. I am excited to present on a fundamental yet fascinating topic in electrical engineering, the speed torque characteristics of DC motor. This presentation will dwell into the behavior of DC motors under varying loads, focusing on two key types, that is separately excited DC motors and series DC motors. By the end of this session, you will have a clear understanding of how these motors operate, their unique characteristics, and their applications in real-world scenarios. DC motors are the workhorses of many industrial and commercial applications. As we all know, their ability to convert electrical energy into mechanical energy with precision makes them indispensable in various fields ranging from robotics to transportation. However, not all DC motors are created equal. Their performance under different load conditions is governed by their speed-torque characteristics, which we will explore in detail today. Let us begin with the separately excited DC motor. As the name suggests, this motor has separate circuits for the armature and the field winding. This separation allows for independent control of the armature voltage, that is VA, and the field voltage, which is denoted by V small suffix f, which is crucial for achieving precise and speed regulations. So the key variables are VA stands for armature voltage, VF is denoted as field voltage, IA is the armature current, and IF is the field current. Now what are the core equations of it? The back EMF is given by E is equal to Kf into phi into N. That is Kf is nothing but is the constant, flux is phi is the flux, and N is the speed. So this is a very common equation which is known to all the electrical engineers. Then the second equation is about the torque. The torque is given by K suffix T into flux into armature current, where Kt is the torque constant. Likewise in back EMF, Kf was the constant. Now in the third equation, we have the armature voltage, which is denoted by Va. So V suffix A is denoted by armature voltage, which is given by E plus Ia Ra into Va. So that is nothing but Va is equal to E plus Ia into Ra, where Ia is the armature current, Ra is the armature resistance. Now we will see the separately excited DC motor speed torque relationship. In a separately excited DC motor, the field voltage Vf is kept constant, which means the flux phi is also constant. This leads to a linear relationship between speed and torque. The speed equation, as we all know, is given by N is equal to Va minus Ia Ra. So the impact of armature resistance Ra. So what can be the impact of this resistance? If the armature resistance is small, that is Ra, if it is small, the speed remains nearly constant even under varying load conditions. This is significant advantage in applications requiring precise speed control. What are the advantages of it? The advantages are wide speed control range, constant torque, and the third is it is ideal for industrial drives and machining tools. Now coming to the next slide, we will see our attention is now to the DC series motor. Unlike the separately excited motor, the series motor has its armature and field windings connected in series. This means the same current flows through both the armature and the field winding, leading to some unique characteristics. Now let us see the key equations. The key equations is given by E is equal to Ks into I into N. Now Ks is the constant, I is the current. Similarly, in the torque, T is equal to Kt, which is nothing but the torque constant, into current. Notice that this torque is proportional. It is nothing but I square into T. This torque is proportional to the square of the current, which gives the series motor its high starting torque. Now, what is the speed equation? The speed equation is given by N is equal to V minus I into the bracket Ra plus Rs. That is, this Ra is nothing but it is the armature resistance and Rs is the series resistance. Since it is a series motor, we have to add up these two resistance, that is Ra plus Rs has to be multiplied by the current, and Ks, which is nothing but it is the speed, it is the constant, series constant, and therefore here you can see Rs is the series field resistance, Ra is the armature resistance, I is the current. So this is the relationship of the speed equation, torque and the back EMF. Now the next slide is deals with the speed torque relationship. In a series motor, the flux phi is proportional to the current I. This results in a non-linear speed torque relationship. As the load increases, you can see the current increases, which in turn increases the flux. This causes the speed to drop significantly as the torque increases. Now we will see the characteristics. Now what are the characteristics? The characteristics are, first is the high starting torque. Due to the initial high current, series motors are excellent for applications requiring high starting torque such as locomotives and starter motors. Then speed variation. The speed varies greatly with the load, making it unsuitable for applications requiring constant speed. The third point is it is no load danger. At no load, the speed can become dangerously high, which is why series motors must always be operated under load. Now we will see the applications. What are the applications? Given their high starting torque and variable speed characteristics, series motors are commonly used in locomotives where high torque is needed to start heavy trains, starter motors in automobiles where high initial torque is required to start the engine, cranes and hoists where heavy loads need to be lifted. Let us summarize the key differences between these two types of motors. Now we will see the separately excited DC motor and series DC motor. In separately excited DC motor, we have constant speed under varying loads, wide speed control range, and these motors are ideal for industrial drives and machine tools. Whereas in DC series motor, speed is always dependent on the torque. So high starting torque, this is used in locomotives and starter motors. The choice between these motors depends on the specific requirements of the application, particularly the need for speed control versus starting torque. In conclusion, we will see that understanding the speed torque characteristics of DC motors is very important for selecting the right motor for a given application. Separately excited DC motors are ideal for applications requiring constant speed and precise control, while DC series motor excel in scenarios demanding high starting torque. By careful considering the load and operational requirements, engineers can optimize motor performance and ensure efficient, reliable operation. Thank you for your attention. I hope this presentation has provided with your valuable insights. Thanks for watching.